this video, we're going to continue talking about the quantum oscillator. We'll first start by doing a short review of the algebraic solution. Then we'll talk about Hermitian conjugates, then normalizing the solutions for the harmonic oscillator, and finally, the orthogonality of the oscillator solutions. So, if you recall, the ground state solution for the harmonic oscillator is simply given by this. It's psi 0, where the index is 0, starting at 0. It's m omega over pi h bar to the 1/4 power e to the minus m omega over 2h bar times x squared. And its energy is 1/2 h bar omega. The higher energy states you can get by using the raising operator a plus. And so you apply a plus to psi n plus 1, and you get something that's proportional to psi n. We don't know that proportionality constant yet. And then E sub n, the energy of the nth state is n plus 1/2 times h bar omega. And we can lower energy states by using the lowering operator, a minus. So a minus applied to psi n plus 1 gives you psi n, and it lowers the energy as well. Now, the normalization we did for the ground state and the first excited state turns out it's the same thing, and that is, this is the normalization for psi 1. Psi 1 is equal to m omega over pi h bar to the 1/4, and then you have a term here that's the square root of 2m omega over h bar, and then you have x e to the minus m omega over 2h bar x squared, and this is the fully normalized psi 1. Now, that's not the case for all states, and so we need to get a more generalized normalization condition, and hopefully it's an analytic expression that will hold for all states labeled by n. So we can start this process by talking about bringing in the concept of Hermitian conjugates. So we can derive this, the normalization, using the property of a plus minus, which are Hermitian conjugates of one another. And so I'll explain what Hermitian conjugate is in a minute by doing a short derivation. So remember, a plus minus is equal to 1 over the square root of 2h bar m omega minus plus h bar d by dx plus m omega x. So this is IP and this is x operator. Now, if you start with any two functions, f and g, let's write down this particular integral. So this is f star, complex conjugate of f, and then a plus or minus applied to g, all integrated over all space in this is a one-dimensional problem, so it's dx. Well, if we put in the actual values of a plus minus, we have our constant out in front, square root of 1 over h bar m omega. And then here we have f star, and here we have minus plus h bar d by dx plus m omega x applied to g dx. If we now apply integration by parts to the first term in parentheses, so we will say this is dv and this is u. And so by doing integration by parts, we're going to effectively move the derivative from the g to the f star. And then we'll pull the second one to the left because we can pull it through. Because it has no derivatives, we can pull it right through and apply it to f star instead of applying it to g. So the idea is we're going to move this operator, which is an a plus minus, over to f star. Well, that's easy enough. If we take this, you have u dv, this is u dv, and you have v du, and when you apply that, there's a minus sign that comes in. So when you apply that term, this becomes just g, and this turns into plus minus h bar d by dx f star. And we've now pulled that into the complex conjugate because there's no imaginary portion here, so you can just pull it all in without having to change anything. So inside this complex conjugate, we've applied this operator, which is that plus minus h bar d by dx plus m omega x. Now, if you look at that, that's simply converting an a plus minus to an a minus plus. So this means that when you apply to the g on the right, over here, you have a plus minus. When you move this operator over by doing a integration by parts, it becomes an a minus plus applied to f star inside the f star. So what this means is that the a plus converts to a minus and the a minus converts to a plus. And that's the meaning of a Hermitian conjugate. If we move an operator from the ket, which is over here, to the bra, which is over here, it turns into its Hermitian conjugate. And we'll say more about that in chapter 3. But suffice it to say that a minus and a plus are Hermitian conjugates of each other, and that's actually a very important quantity. So now we can actually go through and normalize the wave functions by assuming that, as we know, that the raising and lowering operators produce functions which are proportional to the next wave function up or down the ladder. So a plus applied to psi n will produce psi n plus 1 times some constant c sub n. A minus applied to psi sub n will produce a different constant d sub n and psi n minus 1. So raising gives you c sub n, lowering gives you d sub n. Let's take a look at the following integral. We will apply a plus to psi n on the bra side, put it all in complex conjugate, and we'll apply a plus to psi n on the ket side and integrate it all out. Well, if we look at the left side, we can take this and we get psi n plus 1 star. Here we get psi n plus 1 not starred. And then we get Cn star and Cn, which is the modulus squared of C sub n. And that gives us the 1. Now on the right side, alternatively, what we could do is we could move this operator, which is an A plus, over to the bra side, and it goes to the very left side when we add it in, but it becomes an A minus. So we can manipulate this and make it an A minus A plus psi n, applied all starred, and then psi n. Well, what does that do? Well, A plus A minus A plus is related to the Hamiltonian. If you recall, the Hamiltonian, or E sub n times psi sub n, is equal to h bar omega A minus A plus minus a half psi sub n. So this is our Hamiltonian, and A minus A plus is related to it. I can now realize that we know what the energy of the nth state is. It's just h bar omega n plus a half times psi n. And so what that means is that when I apply A minus A plus to psi sub n, I should get n plus 1 times psi sub n, because it goes from a minus 1/2 to a plus 1/2 plus n. And so that has to mean that this operation gives me n plus 1 times psi sub n. We can now substitute this in for the same term over here, and we get that this quantity up here, which is c sub n squared, and then you have the integral, the normalization integral of psi n plus 1, is equal to n plus 1 times the normalization integral for psi n. If we assume that they're both normalized, that means that c sub n squared is just equal to n plus 1. And so that tells us that C sub n is just square root of n plus 1. We can do the same thing with A minus applied to psi sub n. So A minus applied to psi sub n gives me d sub n psi n minus 1. I now make the integral where I apply A minus to both terms, both sides, and then do an integral. And so on the left side here, this gives me d sub n squared and psi n minus 1 modulus squared, integrated out, which is going to be 1 because this has to be normalized. Over here, I'm going to move the A minus over and I get A plus. So now I get A plus A minus psi n, all starred, psi n dx. Well, again, in this case, we can rewrite the Hamiltonian in a slightly different way, in the other form, and that is that E sub n psi sub n is equal to h bar omega A plus A minus plus 1/2 psi sub n. Well, since the energy of the nth state is h bar omega times n plus 1/2, then clearly A plus A minus applied to psi sub n gives us n. So A plus A minus applied to psi sub n gives me n times psi sub n. That means that I can put this back in over here, just like I did before, and I get the modulus squared of d sub n times an integral, which is going to be unit, it's going to be 1, is equal to n times another integral, which is also normalized integral, and also is equal to 1. So this means that d sub n squared is equal to n. So psi sub n plus 1 is equal to 1 over the square root of n plus 1 times A plus applied to psi sub n. And similarly, psi sub n plus n minus 1 is equal to 1 over the square root of n times A minus applied to psi sub n. So those are the rules for what you get when you apply A plus A minus. And this is actually really important. You need to remember this. So using these rules for the coefficients, we can now normalize all the wave functions. So psi sub 1, according to this rule, is just obtained from psi 0 by applying A plus and multiplying times 1 over square root of n. But n is equal to 1, and so this just is 1. Remember, if we have this normalized, then this has the same normalization, and that's not a coincidence at all. It's just because n equals 1 in that case. Similarly, we take psi 2, and we can normalize it by applying this additional factor of 1 over the square root of 2. And if we then repeat that out all the way down to psi 0, we get 1 over the square root of 2 times 1. And then you have A plus applied twice. Similarly, you can go to psi 3, and now you have 1 over the square root of 3 times 2. And this should be A plus, right? And then you have 1 over the square root of 3 times 2 times 1, A plus cubed applied to psi 0. And similarly for the fourth term, we get 1 over the square root of 4 times 3 times 2 times 1, A plus to the fourth psi 0. So in general, we have the rule that psi sub n is equal to 1 over the square root of n factorial times A plus to the nth applied to psi 0. And that's how we can normalize all the functions directly. Now, we can also prove that the solutions to the harmonic oscillator that we've generated in this way are orthogonal. And so we do that, again, by applying a pair of these operators. So we build this integral here, psi star m, A plus A minus psi n. And so these are in the middle. We are now applying the a minus first to psi n, and that gives us the square root of n, and it gives us psi of n minus 1. Then we apply the a plus to psi n minus 1, and we raise it back up to psi n. So now we get psi n, but now we have to get the square root of this plus 1, which is just another square root of n. So 2 square roots of n give me n. And alternatively, we can take this a plus and move it over to the psi m star. And again, it changes to its Hermitian conjugate, so it becomes an a, instead of an a plus, it becomes an a minus. And then we do the next one, we move the a minus over and becomes a plus. So now we have a plus a minus. Notice that when you do the Hermitian conjugates in this trick, what originally was a plus a minus becomes a plus a minus again on the other side. It stays the same, but it's inside the complex conjugate. And this is now applied to psi m. Well, again, we can do that. But first, when we apply a minus, we get square root of m times psi m minus 1. We then apply the a plus, we get another factor of m, square root of m in front. So now we have m times the integral of psi star m psi n dx. So you look at these and you realize that these two integrals are identical. And we've derived everything from the same original form. And so the only way these can be equal is if n is equal to m. If n is not equal to m, then these two integrals must be 0, because that's the only way you can make them equal if the two integers are not the same. So we can express this orthogonality condition. This means that all the psi n's are orthogonal to each other. Whoops. And we can write this down as integral of psi m star psi n dx is equal to the Kronecker delta of nm.